All right, I think we're on.
Alright, hello, welcome back to another Mathcounts meeting. Today we're on 1990 state sprint number 23. Find the length of the line segment with endpoints a comma a and 9a comma 7a, and a is positive. So because a is positive, we're going to be in the first quadrant, and we're going to have some point a here, and then we're going to have some point like 9a, 7a here. We want to find the length of this line segment. So what we know is that this height is a, and this horizontal length is also a by the coordinates of this point. And the coordinates of this point is 9a, 7a. So that we know this horizontal length is going to be 9a. And this vertical length is going to be 7a. And what we're trying to find here is this length right here, and then this length right here, so that if we have those two lengths, we can use the Pythagorean theorem and get the length of the line segment between them. And then to get these lengths, it's not too hard. You just do, for this horizontal line segment, you do 9a minus a to get you AA. And then for this vertical one, you do 7a minus 8, I'll give you 6a. And now we have those lengths, we just need to use the Pythagorean theorem. So AA squared plus 6a squared equals, let's call this x squared. And then you just expand it out. This will be 100a squared. And then you square root both sides to get 10a equals x. So the length is going to be 10a, and that's your answer. So once you get AA and 6a, you can notice that 6 and 8 are 6, 8, and 10 is a Pythagorean triple, right? So that will save you some time. Because the 6 and 8 are being multiplied by a, the 10 is going to be multiplied by a as well. Now, instead of having to go through this process every time, you could just do like the x coordinates minus each other and the y coordinates minus each other, and then use the Pythagorean theorem on that. So yeah, anything you want to say, Bill?
No, but except that this is like a really basic Pythagorean triple. You shouldn't have to use Pythagorean's theorem on this because of just how basic of a Pythagorean triple this is. It's 3, 4, 5. So
Yeah,
this one should be something that you
yeah, you guys should know your Pythagorean triples. That will likely save you some time on the tests. So let's just go over common Pythagorean triples. So we have 3, 4, 5. And so with okay, this is the most basic Pythagorean triple. And with any Pythagorean triple that you have, you can multiply by constants to get new Pythagorean triples. So if we multiply this by 2, we get a new Pythagorean triple, 6, 8, 10, which is what we used here. And then, you can multiply by 3 to get 9, 12, 15, which is another Pythagorean triple. Now, because these three numbers don't share a common factor, it's called a primitive Pythagorean triples. So what you want to do is you want to memorize just the primitive Pythagorean triples, and then you can get a lot of other Pythagorean triples with that. So like if you ever see like 6 and 8, right, and like let's say you didn't know that Pythagorean triple, you want to look if there are any common factors between the two, and then if there are, then you want to like divide by that. So like 6 and 8 have a common factor of 2, so you divide by 2, so you have 4 and 3, right? And then you notice, oh, it's a 3, 4, 5, right? Because you divided by 2, you need to multiply the 5 by 2 to get 10, and there's also a common factor of a, so you multiply a by. Um, yeah, anything. Okay. Let's list out the common Pythagorean triples. So we have 3, 4, 5. We have 5, 12, 13. We have 7, 24, 25. And we have 9, 40, 41. Although that one is pretty uncommon. Any others? 8, 15,
Yeah,
17.
I was about to say the 8, 15, 17.
Um,
I think that's really all the lower ones.
20, 20, 21, 29.
Yeah.
There's
I mean,
also
that I highly doubt 21,
35.
29 will show up.
Okay, yeah. So the
The
ones
common
you
ones is probably just probably not
so
even the
okay,
9,
so
40, 41.
definitely okay, so definitely 3, 4, 5.
3,
Like
4,
that is
5.
extremely common.
Yes.
5, 12, 13 is also extremely common.
Yes.
7, 24, 25, it's less common but will show up.
Yes.
It's kind of the same with 8, 15, 17.
Yes. 9, 40,
And then the
41's
other
probably
ones,
not going to show up.
yeah, the other ones I don't even think I've seen really. I mean, like a few times, but like
Yeah,
barely.
very few times. The other
Yeah.
ones, yeah.
Yeah. Uh, so yeah, these. Okay, and then number 24, a manufacturing company identifies its products by codes consisting of a letter A through Z, followed by 3 digits, 0 through 9, followed by another letter. How many different products can the company manufacture before it uses up all possible codes? Okay, so it's going to have a letter and then 3 digits and then another letter. And that's all of its like properties. Like it doesn't say you can't have repeating digits or letters or whatever. So this should be pretty easy. So you have 26 possibilities of a letter, right? And you have 10 possibilities of digits. It says the 0 through 9, so that's going to be 10 digits. And again, it doesn't have anything else that it says you have to do. So it's just going to be 26 for each of the letters, 26 possibilities for each of the letters, and 10 possibilities for each of the digits. And then with these possibilities, you just need to multiply all of them together to get the total number of possibilities for this for these codes. And that will be 26 squared times 1000. 26 squared is going to be what? Like 625 plus 25 plus 26, which is just 676. So it's 676,000. Um, you can just get this by multiplying it out. Um, yeah, this should be pretty easy. Okay, let's just move on. Find the sum of the first 14 terms of the arithmetic series 2 plus 5 plus 8 plus so on. So again, arithmetic sequences are sequences that numbers differ by some constant value, and in this case, it's by plus 3 every term. Now, if we're looking for the sum of an arithmetic sequence, it's going to be the median or mean of the sequence, because they equal the same thing in the arithmetic sequence, and then times the number of terms. So number of terms is pretty easy. It tells us it's going to be 14 terms, and then we need to find the median or mean. So to find the median or mean, what we can do is take the last number in the sequence and then subtract it, or like, okay, take the last number of the sequence and then average it with the first number in the sequence. So if we find the last number in the sequence, we can get this. So how we can do that is by using this common constant adding thing here. So because it's the 14th term, it's going to be the first term, the value of the 14th term is going to be the first term plus 13, which is this number minus 1 times the common difference. So why is it like this? Well, think about like the second term, right? The second term is going to be the first term plus 1 times the common difference, and 1 is uh, the n2 minus 1. And then so on the third term, it's going to be 2 times 3 because you're adding another 3. So yeah, the 14th term is going to be this value, which is just 2 plus 29, 39, my bad, equals 41. So yeah, and to get median or mean, you take the average of this last term with the first term. So it's going to be 41 plus 2 over 2. And we need to multiply these two terms together. So you can cancel out the dividing by 2 with the 14 to make it 7. And 41 plus 2 is 43. Now just do 43 times 7. So you're going to have 21 and then 28, so 301. Anything you want to say, Bill?
So Austin's method is fine, and it's probably the fastest method you can do. But if you want to like try another method, so what another thing you can do is that you can you can so it is 2 plus 5 plus dot dot dot. What you can notice is that this is the sequence is if you add 1 to each term, it's 3 plus 6 plus 9 plus dot dot dot, which is 1 plus 2 plus 3, and then plus dot 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 plus 14, because there are 14 terms. And so for this, and then 3 times this. And so the thing in here, that's relatively easy to calculate. I mean, not really, but you because here you know what the last term is, and you know what the first term will be, and 1 to 4, 1 plus all the way to 14, that will be 14 times 15 over 2, which is equal to 7 times 15, which is 105. So you know this is equal to 105, and this is equal to 105, and in here every term is low. Oh wait, so this part is equal to 105, and then 105 times 3, that is 315. And so we know that it's 315, but also every term, to get to this, we've added 1 to every single term. So if we take 1 from every single term, you get, there's 14 terms, so you take away 14, so you get 301.
Yeah. Okay. Let's just move on. Um, the first four gymnastic judges gave Mary scores of those, and then what score expresses a decimal number that you need to get from the fifth judge to get an average score of 9.45. Okay, so the four scores that she got were these, and then let's say the fifth score that she needs to get. Oh gosh. Uh, let's say the fifth score that she needs to get is X, and it says that she needs to have the average of these scores 9.45. And what is average? Well, average is just you sum all of these and then you divide it by the number of terms that you have, which is 5 in this case. And so if this is an average and it says that she needs the average score to be 9.45, you can equal this to 9.45. And then now this is just, you can just solve it for X, right? So let's sum all of these first. So, okay, I'm going to take the 9 out of all of these. That's going to be 9 times 4, that's 36. And then we're just summing the decimal parts. So 0.25, 0.4, 0.3, 0.45. It's going to be 0, 1, and that's going to be 8, 10, 14. So 1.40, and we had 36, so that's going to be 37.4. This is Emily. Okay, so that sum is going to be 37.4. So we have 37.4 plus x over 5 equals 9.45, multiplied by 5 on both sides. So we're going to get 9.45 times 5, so 5, 2, 22, and then 45. Nope, 47. You carry the 2 from before. Sorry. Okay, so this is going to be 47.25 here. And then we have 37.4 plus x here. And now you just need to subtract 37.4 from 47.25. And then you get 5, so you need to carry this. So that's going to be 3, and that's going to be 12, and that's going to be 9. So then we have 2, 8, 2.85. So x equals 2.85. I did something wrong. So the actual answer is 9.85.
I think you subtracted wrong.
Yeah.
What? How did you get 2?
Okay. Uh,
How did you mess up
let's
so
do the
badly?
subtraction again. We get 6 here, and then we get 16 here. So that's going to be 9.85. Yeah, I don't know, I'm bad. So x equals 9.85. Oh, anything you want to say, bro?
No. I mean, that's the only way you can do that problem, so there's not really any other way to do it.
Yeah, sure. Um, it took 24 workers working 10 hours per day for 24 days to complete a task. At this rate, how many days will it take 60 workers to complete the same task, working 8 hours per day? Okay, interesting. So to complete this one task, it took 24 workers, 10 hours. So I'll denote workers by W, hours by H, and 24 days by D. And all of this completed one task. And at this rate, how many days will it take 60 workers to complete the same task working 8 hours per day? And we want to know how many days it's going to take. So all of these numbers are going to be proportional to like directly proportional to your task finishing thing, right? Like if you increase the amount of workers, it's going to increase your tasks done proportionally. And same thing with hours, and same thing with days. Uh, I don't know. Is there any way? Is there any other way to explain that? So like, so your time here. This is time, right? So time is obviously going to be proportional to
How much you work?
your task finishing,
Yeah.
right?
Yeah.
Because your task is like some amount of time that you need to take, right? And the amount of workers is also just connected to the time, right? It's like how many times you're speeding the time up, right? Because you have like multiple workers like doing it, right? Okay, so with knowing that all these are going to be directly proportional to the time, we can say that we have some workers times some hours times some days times some proportionality constant, let's call that K, and that's going to equal some amount of tasks. Now, we're given this first set of numbers here. So we can use that in our equation, and then we can solve for the proportionality constant k. So we would get k times 24 times 10 times 24 equals 1. So then we get k equals 1 over 24 squared times 10. Okay, and then now we know k, we can use it to solve for this stuff right here. So it also tells us that it needs to finish one task. So use the same equation, k times w times h times t equals t. And just plug everything in. K is 1 over 24 squared times 10. W is 60. H is 8. And d is what we're trying to figure out. And it equals 1. So if we move everything to this side and keep d on this side, we're going to get d equals 24 squared times 10 over 60 times 8. Now you just need to cancel stuff out. So you're going to get zeros cancel out there. And then, so if we take 6 to be 2 times 3, 3 and 8 is going to be 24. So you can cancel out a 24 like that. And then 24 over 2 is 12. So it's going to take 12 days. Yep, 12 days. Okay, so what another way you can do it is like just looking at like these ratios directly. So like the ratio of this, the ratio of this to this is 60 over 24. And then the ratio of this to this is going to be 8 over 10. And the multiplication of all of these ratios have to be 1. So, and this ratio over this ratio is 1 over 1. So if you multiply all of these ratios, it has to give you 1. So, okay, let's just multiply these. So, okay, if we call this ratio x, then we get 60 times 24 times 8 over 10 times x equals 1. Yep, okay, and then so cancel out 24 and 8 to get 3 here. Cancel out this and this to get 6 on top. And then 6 over 3 is 2. 2x equals 1, or x equals 1/2. So our ratio thing was this over that. So if this over that equals 1/2, then this must be 1/2 of that. So then this equals 12 days. Anything you want to say, Bill?
Not particularly, no.
So, okay, so why all of these ratios multiply to 1 is because this is 1. So if this ratio was like 2, then all of these ratios have to multiply by 2. And so why it's like that is because, again, they're all proportional to the task, the number of tasks you get done. All right, let's just move on. The 8th grade basketball team averaged P points per game in the X Games it won this season. The team scored a total of T points during the season, expressed the total number of points scored in the games it lost in terms of P, X, and T. Okay, so X is the games it won this season, and P is the points per game it averaged in the games it won. So the points that they got from their winning games is PX. but they scored a total number of T points. They scored a total number of T points, then the total number of points that they scored minus the points that they scored in their winning games is the points that they scored in their losing games. And it wants the total number of points scored in the losing games, so it's just T minus PX. That is pretty straightforward. K is the smallest positive integer satisfying these properties. When k is divided by 5, the remainder is 4. When k is divided by 8, the remainder is 2. When k is divided by 11, the remainder is 1. K is what? Um, okay, so what is this, okay, so whenever you divide by something and you have a remainder, there's a special function for that. It's called modulus, and it's denoted with a percent sign. So like if you had, I don't know, 17 modulus 3, this means the remainder of 17 divided by 3. The remainder of 17 divided by 3 is going to be 2 because 3 goes into 15 and 17 is 2 bigger than 15. So all of these are just modulus equations. So we have k modulus 5 is 4, k modulus 8 is 2, and k modulus 11 is 1. Now, now you could solve this by hand, by like testing out values. So like if you're testing out values, you'd want to use the modulus equation with the highest uh I don't know what term this is called, but the highest term that is doing the modulus. So like we would use this, right? So if k modulus 11 equals 1, then k has to be 1 higher than all the multiples of 11. So then, we could list that out. That would be 1, 12, 23, 34, 45, and so on. And then we can try these out in here. So if k modulus 5 is equal to 4, then k has to be 1 less than a multiple of 5, right? So if we look at this, what is 1 less than a multiple of 5? Well, 34 is 4 less than a multiple, or 1 less than a multiple of 5. And we can test 34 to see if it satisfies this constraint, which it does because 32 is a multiple of 8. And then should we actually solve it by modular arithmetic?
Solving it by modular would that is definitely like the slower way to go about this. Um, in this case, I would suggest just not bothering with actual like rigorous solving and just trying out numbers in this case.
Yeah, I think it would be faster just trying out numbers. So yeah, so we're just gonna leave it at that. Oh, why is that worked out? Okay. Okay, number 30, the area of a semicircular region is 49/8 pi square inches. Express the number of inches in the perimeter of the semicircular region to the nearest whole number. Okay. Wait, what? Looks like they had some kind of typing error. So that part of the problem we saw in a different problem earlier, right? So
Yes, it was technical error.
I'm guessing the problem is just the thing that they marked out there.
So yeah, what is the problem? So we've already saw the bottom part of
What?
Oh wait, yeah, the thing they marked out is yeah, okay. Yeah, that's no
Yeah,
problem.
I don't know why they marked that out, but okay, so the area of a semicircular region, we have a semicircle, is 49/8 pi square inches. And we need to find the number of inches in the perimeter of the semicircular region to the nearest whole number. And it says to the nearest whole number again. Okay. Um, okay, so so we obviously need to find what the perimeter is, right? And then round it. So let's do that. So let's call the radius of the semicircle r. Now, if the radius of the semicircle is r, then the area of the semicircle is going to be pi r squared over 2, right? Because the area of the entire circle would be pi r squared. Semicircle is half of the area of the circle, so half of pi r squared. And this equals 49/8 pi square inches. So we can cancel out the pi's. And if we move the 2 to this side, then it's going to cancel with the 8 so that it's dividing by 4. So then r squared equals 49/4 inches squared. And then we square root both sides. R is going to equal 49 is 7 squared, so 7, and 4 squared is 2, so 2. So 7 has inches. Okay, so if the radius is 7.5 inches, we already know what the length of this segment is going to be. That's going to be 2r. And we just need to find the length of this segment. Well, we can easily do that by thinking of like the circumference, and that this arc length will be the circumference over 2. So the entire circumference is going to be the diameter, which is 2r, times pi. So pi, 2 pi r, 2r pi, sure. And, again, we have a semicircle. The arc length of the semicircle is going to be half of the circumference of the entire circle. So 2 r pi over 2. So the 2's are going to cancel. That's just our pi r. So this length is pi r, this length is 2r. The entire perimeter is going to be 2r plus pi r, or 2 plus pi times r. Now we figured out what r was, so our perimeter is going to be 2 plus pi times 7/2. So, and we want this to the nearest whole number, right? Okay, so if we expand the 7/2, we have 7 plus 7/2 pi. Now, because 7 is a whole number, we just need to round this to the nearest whole number and then add that by 7. So let's figure that out. 7/2 times pi. So I would first estimate pi to be 3. And if it's somewhat close to, if it's somewhat if it's somewhat in between a whole number so that like its decimal is close to 0.5, then I would estimate pi to be more precise. But let's just work with 3 for now. So if we have 3, that's going to be, or 7/2 is just 3.5, right? So then we have 3.5 times 3, and 3.5 times 3 is just going to be 9 times 9 plus 1.5, or 10.5. And then look at that, that is it's on the very edge of rounding between like 10 and 11, right? So then we should estimate pi to more digits. So let's estimate pi to 3.1. So now we're gonna have, so if you want to do this faster, you can think of it like when we estimated pi to be 3, we're estimating it lower than it actually is, right? And then when you add on the stuff, it's going to be more than this. So then it would round to 11. And it's not going to be large enough to round to the next whole number because it's like 0.14 stuff. And then 0.14 stuff times 3.5 is not going to be 1 or greater than 1. So then you can just say it's 11. And then 7 plus 11 is 18. Now, you can calculate it if you want to. So, if you estimated pi to be, let's just go with 3.14, that would take a little bit more work, but you could definitely do it. So that'd be 20, and then that'd be 5, that'd be 15, and then that'd be 12, that'd be 3 plus 1 is 4, that'd be 9, and then it's going to be 9, 9, 10. Okay, oh, whoops, right here. And so when we estimate pi to be 3.14, then we get it equals 10.99, and that is very close to 11. So we can say it's 11, and if we add on more digits, it's likely not going to push this all the way to 11.5. So then you do 7 plus 11 and you get 18. Anything you want to add, Bill?
Oh, in this case, no.
Okay. Yeah. All right. That was all of the sprint problems of 1990 state. So let's move on to the target problems. Um, all right. So RB spent $56 for pizzas for the math team. If the pizzas had been purchased, what? Okay, sorry. Um, if the pizzas had been purchased at another pizza parlor where the purchase price per pizza was $1 less, the team could have purchased one more pizza. How many dollars did RB pay per pizza? Okay, so initially, RB spent $56 for pizzas. Let's just call it some X amount of pizzas. Now, so then we have a new thing, and the price per pizza is $1 less. Okay, why don't we call the price per pizza is Y? Okay, so in this other pizza parlor, the price per pizza is $1 less, so it's going to be 1 minus 1. And okay, the team could have purchased one more pizza. Okay, so I mean, we can't really say that they use the same amount of money, right?
Um, well, you probably
No, I mean like they could have okay.
I think in this case they're wanting you to use, the same amount of money. Because if not, there's no real way to do the problem. Because
Yeah, sure.
yeah, because otherwise you could just have an arbitrarily high amount of money and you can't really do anything with it. So
Okay. Yeah, sure. Let's assume that they do use the same amount of money, which they probably are, which is what they probably want us to do. Okay, and they could purchase one more pizza, so X plus 1. So how these numbers are related in a way. So if you have the total amount of money you paid, and then you divide it by the number of pizzas you have, then you get the price per pizza, or Y. So, you can express Y as just 56 over X, $56 over X. And then so this is just going to be $56 over X minus 1. And then you can use the same thing here. So then you have $56 over X plus 1 equals $56 over X minus 1. Now, is this a good way to do it? Let's just try solving it this way. So multiply by x plus 1 on both sides. Okay, and then we need to expand it. So x times $56 over x is going to be $56. And then that is going to be plus 1 times $56 over x, which is just that. And then x times -1 is minus x, and the 1 times -1 is minus 1. So the $56 cancel out. Then you have, let's move this over here. So then you have x plus 1 equals $56. And then you have over x. And then you have x squared plus x equals $56. Then you have a quadratic equation. So we have x squared plus x minus $56 equals 0. So x is going to equal, just use the quadratic formula. So negative b, so -1, plus or minus the square root of b squared, so 1 squared. And then you subtract 4 times a times c, so a is 1, c is negative $56. I'm not going to put dollars anymore. And it's going to be over 2a is 1, so 2. And then the stuff is going to be 1 plus 4 times 56. So that's going to be 24, 22, 224. And that gives us 225. So this is the square root of 225, or 15. All right, now x, so it's -1 plus or minus 15 over 2. Now x can't be negative, right? Because you can't have a negative, you can't buy a negative number of pizzas. So we're not going to do the minus 15, we're going to do the plus 15. So then we have -1 plus 15, that's 14. And then over 2, that's 7. Okay, so in this new case, they bought 7 pizzas. So if they bought 7 pizzas with $56, then that means the dollars per pizza was $56 over the number of pizzas they bought, or 7. So that equals $8. And that is your answer. Anything you want to say, Bill?
Okay, so first of all, if we go back and look at the quadratic, you could have just factored that quadratic into x plus a and x minus 7.
Sure.
And also, if you just look at the question itself, 56, if you notice, 56 is 7 times a, and so at the next pizza parlor, or the price went up one, no, the price went down one, and the number of pizzas went up one. So seven, if the price and the number of pizzas they bought were 8 and 7, if one went up one went down one, they would just switch, and you would still be left with $56. So I mean, so a fast way to do this is just basically noticing that 7 and 8 were one apart, and so you could just use that and find that it was $8.
Yeah, sure. Okay. Let's move on. So we have find the smallest positive integer divisible by 2, 3, 7, 10, 15, 20, 21, and 28. So basically we're finding the least common multiple of all of these numbers. Right? Yep. So, so if you're finding the least common multiple of a set of numbers, we said this like multiple times before. What you want to do is you want to prime factorize all of the numbers. So we're going to get 2 times 5 for 10, 3 times 5 for 15, 2 squared times 5 for, oh, my pen. 2 squared times 5 for 20, 3 times 7 for 21, whoops. 3 times 7 for 21, and then 2 squared times 7 for 28. And once you've prime factorized these, and you're taking the least common multiple of these, you want to look at all of the primes, and you want to take the greatest power that any of the numbers have of the primes, and that will be the power prime in your least common multiple. So let's look at 2. So you look at all of these numbers and you look at what's the highest power 2 that any of these guys have. It's going to be 2 squared. So that means our least common multiple has to have 2 squared. And then you look at 3. The highest power 3 is just 3 to the first. You look at 5. Highest power 5 is 5 to the first. You look at 7. The highest power 7 is 7 to the first. And there are no primes after that. So this is going to be our least common multiple, which is 4 times 3 times 5 times 7. The 4 and 5 is 20, and the 3 and 7 is 21. That is just 420. Okay, anything you want to say, Bill?
No.
Okay. We want to express this as a common fraction. It might seem a little bit daunting at first, but it shouldn't be too bad. So, okay, so let's talk about negative and fractional powers, if you guys don't already know. Hold on, let me write this out first. All right. So negative and fraction powers, if you have some x and you're taking it some fraction power, let's say 1 over y, then this is just meaning the yth root of x. So, if you had 4 to the 1/2 power, this is the square root of 4, which is 2. Now, negative powers, if you have x and negative y, this is just 1 over x to the y. So if you had 4 to the negative 2 power, that's just 1 over 4 squared, which is 1 over 16. So we have to the negative first power, so that's going to be this fraction. It's going to be 1 over this fraction to the first power. Now, the fraction to the first power is just the fraction, right? So we're going to have 1 over the fraction. Now, if you have 1 over a fraction, it's going to be the reciprocal of the fraction. So we just have to take the reciprocal of all these fractions, which is just 2 and 3, and 5 and 7. And then that's the negative first power. And that is going to be 3 plus 7 is 10, 2 plus 5 is 7, and that's going to be 17. So 17 to the negative first power. And by what we said before, this is going to be 1 over 17 to the first power, or 1 over 17. So that's your answer, 1 over 17. Okay, given the operations, that stuff, we have to evaluate something. Okay, so let's just do that. So what these lines mean, this is a common function. This is the absolute value function. So if you have absolute value of x, it is defined as the piecewise function x when x is greater than or equal to 0, and it's x negative x, sorry, when x is less than 0. So, if you think of it graphically, it looks like this, right? And it's just taking like the positive value of x. If x is positive, then it's just x. If x is negative, then you negate it again to get its positive value. Okay, and then so let's just evaluate that, right? So we have 6 at the absolute value of 3 hashtag 9. So let's evaluate 3 hashtag 9. So we're given a hashtag b equals 2a minus b. So 3 hashtag 9 is going to be 2 times 3 minus 9. And that is just going to be 6 times 9, 6 minus 9, negative 3. So now we have 6 at absolute value of negative 3. Well, absolute value of negative 3, that's 3. You're just taking the positive value of it. So we have 6 at 3. Now, 6 at 3, we're given a at b is a plus b over b. So 6 at 3 is 6 plus 3 over 3. So that's just 9 over 3. That's just 3. Okay. How many how many natural numbers that are not prime are factors of 8, 5, 7, 5? Okay. Interesting. So we're looking at the factors of 8, 5, 7, 5, the number of factors that it has, but not prime. Okay, how are you going to do this?
So, well, you can prime factorize them and then just take away one from each, like one from each factor. Like if you prime factorize them and you take out one of each factor. Do you get what I'm saying here?
Okay, that factor formula thing.
Yeah.
So like you prime factorize it and then you subtract 1 from each factor and you
Yeah.
raise it to the same power.
Wait, no. What? No, I'm saying like subtract one from the power. Would that work?
Uh, I mean, we can like test it. So we have 12.
Yes.
How many
So
factors does 12 have? It's
yeah.
going to
So
be,
here.
it counts 1, right?
Yeah.
So 1, 2, 4, or 3,
Yeah. So uh,
4,
whenever you're
6,
doing
12,
problems, if you're not sure
6.
about something, you can always just check it on a smaller scale first to test like a theory or like try and try a method that you want to try.
Uh,
Do it on a smaller
you're
scale.
saying subtract 1 from the powers and do it to that power?
Yeah, now that I'm looking at it, that doesn't seem like a good idea. Yeah.
What was the formula?
I mean, we can always just find how many factors there are in total and then just subtract away the the primes. We can just prime factorize 8575.
Wait, what?
We can just prime factorize 8575 and then just like manually sub and then find all the factors of
Yeah,
8075.
I think we should use the factors formula, but we're just bad
You
because we
can try.
forgot it.
You can do that. I mean, sure.
Um. Okay, it looks like. Uh. Yeah. Hold on. How did I forget the formula? All right. Okay, so it seems like the total number of factors for n is going to be the exponent of the primes plus 1, and you multiply those together. So in this case, it would be 2 plus 1. So this is the power of 2, and you add 1 to it, and then the power of 3, which is 1, and you add 1 to it as well, and you multiply those, then it's 3 times 2, 6. So that is the formula for total number of factors for n. So let me just write it.
Right, that's what I was saying. We can use the equation for finding the total factors and then taking away like the ones that are prime.
Okay. So yeah. So what the formula is saying. So if we have a number n and then we prime factorize it, to some like, let's just say, I don't even know. Let's just say x to the a, y to the b, and z to the c. So then the total number of factors is going to be a plus 1 times b plus 1 times c plus 1. And if you have more primes, then you just continue that. Now, there are more formulas that you should probably know, I think. So sum of factors. Let me look at this here. Hold on. Okay, that's much better. So yeah, the formula for the sum of the factors of, like, let's say this n number, it's going to be this x to the 8th power plus x to the a minus 1 power plus x to the a minus 2 power, and then plus dot dot dot, and you get all the way to plus x to the first plus x to the 0th. And then you do that with the other things as well. So it's going to be the same thing for y and z. So y to the a plus dot 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 plus y to the 0th, and it's going to be z to the, oh, not a, sorry. It's going to be b for this, for y, and it's going to be c for z. So z to the c plus z to the c minus 1 plus dot 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 plus z to the 0th. So like in this case with 12, prime factorization of 2 squared and 3, the sum of the factors would be 2 squared plus 2 to the first plus 2 to the 0th times 3 to the first plus 3 to the 0th. Now 2 squared is 4, 2 to the 1 is 2, to anything to the 0th power is 1, and then 3 to the first is 3, 3 to the 0th is 1. So then the sum of the factors of 12 is going to be 7 times 4, or 28. And then, you can test that by adding these. That's going to be 6 and 4 is going to be 10. And then this is going to be 6. This is going to be 12. 6 plus 12 is 18. 18 plus 10 is 28. So in this problem, we're just doing the total number of factors, but the sum of factors might show up sometimes. So you might want to know that formula as well. All right, but we're just finding the total number of factors that are not prime. And so how we'll do that is find the total number of factors with this formula and then just subtract how many primes it has in its prime factorization. So we're going to need a prime factorizer first. So divide this by 5, you're going to get 1715. You can get another 5 out of it. Divide that by 5, you'll get 343. And then 343 is going to be 7 cubed, I think. So if we take out a 7 there, that's going to be 4. 63 is 9. And 49 is going to be 77. So if you didn't know that 343 was 7 cubed, then you could just like test some primes that go into 343, and 7 is pretty low, so yeah. Okay, so our prime factorization of 8575 is 5 squared times 7 cubed. So the total number of factors is going to be this exponent plus 1 times this exponent plus 1. So that's 3 times 4, 12. That seems a little bit deceiving, that this big of a number only has 12 factors, but it does. So this is the total number of factors that it has. And then we want to find the total number of factors that are not prime. So, but we have 2 different prime factors, right? So we minus 2 from that, and you get 10, and that's our answer. Anything you want to say, Bill?
No. So yeah, in this case, just find all the factors and then take away the numbers that are prime. There is
Yeah.
probably like a other way to do this, but this is definitely like the fastest way to do it. Sometimes like the bashy way is the more faster way to do it.
Yeah.
Probably do
And
something like with the factors or something, and then like just make them take away the prime numbers, but that's gonna be slow. So this will be the fastest one.
yeah, these formulas will be useful, so you should probably memorize them. Like yeah, but we're bad, so we didn't have them memorized. But yeah, we're pretty over time now, so that's going to be it. Thanks for watching, and goodbye.